Section: Introduction. In this section, we discuss transformer-based language models, which have shown to be highly effective at generating sequences. With ample training data and computational power, these models can learn intricate patterns, leading to impressive capabilities. Recent studies indicate that when given enough context and reasoning ability, these models can pick up new patterns without further training, a process known as in-context learning. Despite their success, understanding the specific patterns these models learn and their learning processes remains challenging. We find pseudo-random number generators, PRNGs, to be a compelling case for examining these issues. PRNGs are crucial in cryptography and computer science, designed to produce outputs that seem random but are based on mathematical patterns that powerful sequence models might learn. This raises important questions about the abilities and limitations of transformers. Can they predict PRNG outputs with enough training data and context? What does this mean for our understanding of both transformer models and PRNGs? Do they learn the actual algorithms behind the generation, or do they just find shortcuts? We also consider how factors like model capacity, data variety, training methods, and context length influence their capabilities. Our work focuses on learning sequences from linear congruential generators, LCGs, using GPT-style autoregressive transformers. We show that transformers can effectively learn LCGs with moduli up to a specific large number. We conduct interpretability analyses to reveal structures in the model's layers and the algorithms it uses to learn these sequences. Additionally, we perform scaling analyses to explore how architecture and sequence complexity affect performance and in-context learning. We also connect our study to various topics in modern and classic research. We contribute to the understanding of interpretability and modular arithmetic by reverse engineering algorithms and identifying structures in pseudo-random number sequences. While cracking PRNGs is a significant area in cryptography, deep learning approaches have been less explored recently. We analyze more complex cases of unseen parameters with transformers, examining learned algorithms and the impact of scale and complexity. Furthermore, we view LCGs as formal languages within the Chomsky hierarchy, providing a controlled setting to study neural network properties. We also relate PRNGs to chaotic time series predictions, which are vital in fields like weather forecasting and finance. We define LCGs as simple PRNGs that generate sequences based on specific parameters: a modulus, a multiplier, and an increment. The complexity of an LCG sequence is determined by its period, which we show is crucial for prediction difficulty with transformers. We evaluate our models on sequences that meet specific criteria outlined in the Hull-Doble theorem, ensuring they are suitable for our analysis. LCGs are favored for their efficiency and simplicity, often serving as the foundation for more complex PRNGs. While they may struggle with small bit sizes, they perform well with larger states, passing rigorous randomness tests. Section Summary. In this section, we explore the capabilities of transformer models in learning sequences generated by linear congruential generators, LCGs, focusing on their ability to predict outputs based on underlying mathematical patterns. We analyze how model capacity, data variety, and context length influence performance, while also investigating the emergent structures and algorithms that transformers utilize in this learning process. Section: Training Setup. In this section, we describe our training setup for decoder-only transformers, which we use to predict the next number in linear congruential generator, LCG, sequences. The model takes an LCG sequence as input and outputs a sequence where each output matches the next number in the input. To predict an unknown LCG sequence, the transformer must infer the parameters of the LCG, specifically the modulus, multiplier, and increment. We evaluate the model's ability to generalize in two scenarios: fixed modulus, FM, and unseen modulus, In the FM scenario, we train and test on sequences with a constant modulus. In the UM scenario, we train on sequences with varying moduli and test on new, unseen moduli. For dataset generation, we apply the Hull-Dobel theorem to find the best multiplier and increment values for a given modulus, selecting 64 random pairs for our test dataset. For training, we exclude these pairs and sample 100,000 LCG sequences of a specified length, using different multipliers and increments. The training dataset includes sequences with various periods, while the test dataset focuses on those that maximize the period. In the scenario, we reserve a set of test moduli solely for evaluation. We determine the optimal multiplier and increment values for these test moduli and randomly select pairs for the test dataset, ensuring they are not included in the training data. We sample modulus values from a defined range, excluding those reserved for testing, and generate training sequences based on these parameters. We find that having a sufficient number of modulus values relative to the test moduli enhances generalization performance. We set our default configuration for experiments based on this relationship, ensuring we have a balanced number of multipliers and increments. For tokenization, we treat each number as a unique token, adjusting the dictionary size based on the scenario. We utilize GPT-style transformers with learnable positional embeddings and weight tying. When scaling to larger moduli, we limit the dictionary size by tokenizing numbers in a specific base, resulting in fewer tokens per number. Our model architecture includes various parameters such as depth, embedding dimension, and attention heads, and we train using the ADAM-W optimizer and cross-entropy loss. Section Summary. In this section, we describe our training setup for decoder-only transformers, which predict the next number in linear congruential generator, LCG, sequences by inferring parameters in context. We evaluate the model's generalization across two paradigms, fixed modulus, FM, and unseen modulus, using carefully generated training and test datasets, while employing a tokenization strategy and a GPT-style architecture optimized with ADAM-W and cross-entropy loss. Section: Training Results. In this section, we explore the fundamental algorithms that our models use for both the FM and tasks. While there are some differences in the details of these algorithms, they share common characteristics due to the underlying structure of linear congruential generators, LCGs. We begin by discussing the properties of LCG sequences that will help us understand the model behaviors. For an LCG sequence with a modulus of 2048, each number can be represented as an 11-digit binary number. A key feature of LCGs with this modulus is that each digit in the binary representation has a fixed period throughout the sequence. Specifically, for a sequence with a period equal to the modulus, the period of the WTH lowest digit is 2 raised to the power of W. This means that lower digits have shorter periods, while higher digits have longer periods. We will later see that trained transformers develop structures that identify these binary representations and use them for making predictions based on context. The period of each digit significantly impacts the accuracy of its prediction. To illustrate this, we consider a scenario where we skip a certain number of steps in the sequence. In this case, the period of each digit reduces, making higher digits easier to predict, while some lower digits may become constant and trivial to predict. We demonstrate this with our example, showing how the periods of digits change when we skip steps. Transformers can enhance their ability to predict LCG sequences by utilizing these step iterations from the context provided. Longer contexts lead to larger values of the steps skipped, which in turn improves the accuracy of predictions. While moduli of the form 2 raised to a power allow transformers to find binary representations, more complex moduli require a broader representation known as the residual number system, RNS. In the case of composite moduli, we can represent each number uniquely using its values modulo the prime factors of the modulus. Each digit in this representation also has a specific period, which can be reduced through the same step iteration process. We will show that recognizing these RNS representations is a crucial simplification that our transformer models discover when learning LCG sequences. Section Summary. In this section, we investigate the minimal architecture required for transformers to solve two tasks: finding that a single layer and attention head suffice for the FM task, while the task necessitates at least 3 layers and careful hyperparameter tuning. We also reveal that transformers can effectively predict LCG sequences by leveraging binary representations and residual number system representations, simplifying the prediction task through context and iterative steps. Section: Interpretability, Fixed Modulus. In this section, we discuss the algorithm used by transformers trained on linear congruential generators, LCG, with a fixed modulus. We demonstrate that even though we input integers, the model creates and utilizes emergent structures that represent the inputs in a residue number system, RNS. We focus on a setup with a one-layer, single-head transformer trained on LCG with a modulus of 2048. Similar findings for other moduli and model sizes can be found in the appendix. We analyze the average accuracy of the trained transformer model based on the position of tokens in the context. We notice a ladder-like accuracy pattern, with increases occurring at specific token positions that are powers of 2. This pattern can be explained by looking at binary representations and recurrence relations. Specifically, to predict a token at a position that is a power of 2 or greater, the model can refer back to a previous position and apply a recurrence step. This allows the model to copy the lowest bits, which remain unchanged, and simplify the higher bits, as their cycles are reduced. We find that the accuracy trend is consistent across different values of the parameters. Next, we compute the accuracy for each digit by converting model predictions and true labels into binary. We observe that the model predicts more digits correctly with more context, with sharp transitions at the same power of 2 positions. This indicates that the sequences become simpler as the model can look further back and apply the recurrence steps. We then explore how different components of the model implement the algorithm. First, we perform principal components analysis, PCA, on the embedding matrix, revealing how the model organizes numbers based on their binary representations. We see that numbers cluster according to their remainders when divided by powers of 2. Next, we examine the attention weights and find that to predict a number at a certain position, the model focuses most on a specific earlier position that is a power of 2 less. This allows the model to copy the lowest bits and simplify the prediction of higher bits. We conduct experiments to confirm that the brightest attention lines help in copying lower bits, while other lines are essential for predicting higher bits. After the attention layer gathers information, the MLP block processes this data to make predictions. We observe that each neuron in the MLP responds periodically based on the target prediction. We analyze the activation of neurons for a specific token position and see that only a few neurons activate for a given target, showing a strong periodic response. Finally, we visualize the contributions of individual neurons to the prediction. By isolating a single neuron's output, we can see how it contributes to resolving the target number. We find that the periodic patterns from different neurons combine to improve the accuracy of the prediction as we add more contributions. Section Summary. In this section, we analyze a transformer model trained on a linear congruential generator, LCG, with a fixed modulus, demonstrating that it develops emergent structures to leverage the residue number system, RNS, representation of inputs. We observe a ladder-like accuracy structure in predictions, which is explained by the model's ability to utilize binary representations and step iterations, with attention mechanisms focusing on key token positions to effectively copy and simplify bits for accurate predictions. Section: Interpretability, Generalization to Unseen Modulus. In this section, we explore the interpretability of our model when generalizing to unseen moduli. We begin by discussing the qualitative algorithm for unseen modulus, tasks, which differs from the fixed modulus, FM, case. Our training set for is created using various moduli that the model has not encountered during testing. Each modulus has a unique representation, requiring the model to adopt a more flexible algorithm. We analyze how the embedding layer and attention heads of a 4-layer transformer model contribute to solving tasks. Our model is trained on a dataset with specific parameters, ensuring that certain moduli are excluded from the training set to prevent data leakage. We maintain consistency with previous settings by choosing a maximum modulus value. First, we examine the embedding layer. Our PCA analysis shows that the model organizes numbers in a semicircular pattern along the first principal component, while the second component separates even and odd numbers. This semicircular arrangement is reminiscent of patterns in modular arithmetic, but since we use multiple moduli, the model cannot define a single value for 0. Further analysis indicates that the second and third principal components group numbers based on their remainders when divided by 2 and 3. Unlike fixed modulus scenarios, the model does not need to represent numbers in binary form. Instead, it creates representations based on the specific modulus used during testing, facilitated by specialized attention heads. We believe the model's focus on moduli 2 and 3 arises from their prevalence as prime factors in the training data. In the first layer, attention heads categorize numbers by their remainders with various prime factors, allowing the model to build representations that require different prime bases. To investigate this specialization, we analyze the attention heads processing different prime factors. We perform PCA for each head and visualize the results. By inputting sequences with specific modulus values, we extract outputs from individual heads and project them onto the top 2 principal components. This analysis reveals that each head effectively groups numbers based on their remainders with different prime factors, enabling the model to select the appropriate representation. We also assess the impact of pruning specific attention heads on model performance. By replacing outputs from certain heads with their mean values, we observe significant performance drops for digits associated with the pruned heads, while other digits remain relatively unaffected. This confirms the importance of head specialization in the model's ability to compute specific digits. Next, we explore the model's internal uncertainty regarding the relevant RNS representation. We find that the model estimates the testing modulus through a greedy approach, focusing on the largest numbers in the input sequence. Our analysis shows that one attention head consistently aligns its outputs with these larger numbers, indicating its role in estimating the modulus. We conduct patching experiments to further validate this head's influence on performance. By overriding outputs from this head during a forward pass with a different modulus, we observe that the model's predictions shift towards smaller values, confirming its unique contribution to estimating the modulus. Finally, we discuss how the model prepares features and implements the algorithm in subsequent layers. We notice a pattern in digit-wise accuracy that reflects a copying bias, particularly for the lowest digits. By leveraging the estimated modulus value, we argue that the model can accurately predict higher digits without knowing the exact modulus. While the transition from lower to higher digits is evident, the precise mechanism remains unclear. We suggest that the model likely employs an algorithm similar to that used in the FM case for computing these higher bits. Section Summary. In this section, we analyze how a transformer model generalizes to unseen moduli by utilizing specialized attention heads and an embedding layer that groups numbers based on their remainders with respect to various prime factors. We demonstrate that these mechanisms enable the model to effectively construct residue number system representations and estimate the relevant modulus, ultimately influencing its performance on digit-wise tasks. Section: Scaling up the modulus. In this section, we explore the training of transformers by increasing the modulus of linear congruential generators, LCG. To achieve this, we implement several changes. First, we use base B tokenization to manage large dictionary sizes when the modulus is large. This method breaks down each integer into a series of base B digits, starting from the least significant digit, which keeps our vocabulary size at B, regardless of M. We find it advantageous to select B such that the greatest common divisor of B and M equals B. Next, we utilize abacus embeddings to represent positional information. This involves two learnable vectors, one for the integer's position in the sequence and another for the position of each digit within the integer. We provide a visual representation of both base B tokenization and abacus embedding. For fixed modulus, we focus on moduli of the form 2 raised to the power of k, where k ranges from 16 to 32. We train a two-layer model with a model dimension of 1024 and a vocabulary size of 256. We select training sequences based on the Hull-Doble theorem, using specific values for A and C. For testing, we choose different values of A and C from those used in training. The effectiveness of an LCG is largely determined by its multiplier, which we assess using the spectral test. Our results show that while we achieve perfect test accuracy with equal sequence lengths, the model performs worse on sequences generated with optimal Steele multipliers compared to arbitrary ones. We also analyze how the number of in-context sequence elements needed for perfect accuracy grows with the modulus m, finding that it scales sublinearly, approximately as m raised to the power of 1/4. In the case of unseen modulus, we train a 6-layer transformer on a dataset with specific parameters, ensuring the sequence length is 512 and each integer is represented as 2 bytes. We again use unseen values for testing, focusing on moduli of the form 2 raised to k and 3 raised to k. Our findings indicate that the number of in-context elements required for 60% accuracy scales with the test modulus, roughly as m raised to a power between 0.24 and 0.33. We note that the choice of tokenization base affects test performance, as it emphasizes the periodic structure of LCGs, making it easier for the model to learn. To validate this, we train a model using a tokenization base of 243 and observe that sequences of the form 2 raised to k and 3 raised to k show better scaling when the tokenization base is 256 and 243, respectively.